Hello students, welcome to the concepts beam efficiency and bandwidth in antennas. You all know we are in the concepts of antenna parameters. These two are also two antenna parameters. First we'll see the beam efficiency. Beam efficiency is used to judge the quality of transmitting or receiving antenna, and it measures how much amount of the total power gets radiated or received is concentrated within the main beam of the antenna. Okay, what is this main beam? In the radiation pattern concept, I explained that the radiation pattern consists of main lobe and also many minor lobes. Those minor lobes consist of side lobe, back lobes, etc. So now this beam efficiency will measure how much amount of the total power gets concentrated in the main beam. Okay, then what is happening if we find that? Then we can, yes, if the efficiency is high, we can say the power is highly concentrated in the main beam, means the power, there is no wastage of power in the minor lobes. That is the concept of beam efficiency. Coming to the formula, if for an antenna, the major lobe is concentrated along the z-axis. Along the z-axis means theta is equal to 0 direction. The beam efficiency is power transmitted or received within the cone angle θ1 divided by power transmitted or received by the antenna. Means the denominator is total power and the numerator is only the power within the cone angle θ1. Okay, I'll explain the concept. This is the z-axis, and suppose if the main beam is like this and these are some minor lobes. Okay, and what about these points? These are nothing but first nulls at which the radiation is 0. Yes, I explained about the first nulls and the radiation pattern concept and beam width concept also. Yes, now this total is called FNBW, and the angle between this z-axis and FNBW curve is nothing but your θ1. That is called cone angle θ1. So now if you find total power in this cone angle, only in this cone angle, okay, and that becomes the power transmitted or received within the cone angle θ1 divided by the total power. Okay. Then in the form of mathematical formula is to get the power transmitted or received within the cone angle θ1. We know this is the formula. The past videos I explained this also. But as the numerator is the power within cone angle θ1, now the limits of phi limits are 0 to 2 pi, but the theta limits are only 0 to θ1. Because you have to find the power transmitted within the cone angle θ1. Divided by the total power, hence you have to consider the total limits. Theta limits are 0 to pi and phi limits are 0 to 2 pi. Okay, so this is about the beam efficiency mathematical formula. Now these are some points regarding the beam efficiency. θ1 is usually half of first null beam width, and next is while calculating θ1 you have to consider only the main lobe or major lobe, and BA indicates how efficiently power is concentrated in the main lobe. Higher BA means less power wasted in side lobes and back lobes. Explained all these points already. Helps to evaluate antenna focusing ability. Obviously, if all the power gets concentrated in the main lobe, then yes, what is happening? There is no wastage of power, means as the main lobe is entirely consists of the pattern of the power, then the focusing ability of the antenna is very high. Okay, a very high beam efficiency, usually 90% of the efficiency is necessary for antennas used in high-end applications like radiometry, astronomy, radar. And in all these applications, there should not be, in all these applications, the minor lobe consists of, all the minor lobes consist of very less power. Okay, so this is about the antenna beam efficiency. Now we'll move to the antenna bandwidth. What antenna bandwidth is defined as the range of frequencies within which the performance of the antenna with respect to some characteristic conforms to a specified standard. Yes, it is not the general, it is not like general definition of bandwidth. In general, the bandwidth is defined as the difference between upper cutoff frequency and lower cutoff frequency, or This is the difference between two frequencies at which the gain decreases by root 2 times, or the gain in dB decreases by 3 dB. It is not like that. The bandwidth of antenna is defined with respect to some characteristics. Okay, you know the antenna has many characteristics like, see all these characteristics: input impedance, radiation pattern, beam width, polarization, side lobe level, gain, beam direction, radiation efficiency. Yes, with respect to all these characteristics, the bandwidth is defined. Okay, means antenna works properly within the limits only over a certain frequency range. Okay, yes. Then the bandwidth can be considered to be the range of frequencies on either side of a center frequency. You know the concept. See this. Suppose this is frequency, and this is the gain. Suppose if the response is like this. This is the center frequency. I will call it as FC. Okay. Now the bandwidth can be considered to be the range of frequencies on either side of center frequency. Okay. Yes. This side and this side. Okay. These two sides. Okay. The bandwidth is considered to be the range of frequencies on either side of a center frequency where the antenna characteristics, all these characteristics are within an acceptable value of those at the center frequency. Okay. Suppose let it be input impedance at FC. If the input impedance is some let it be 50 ohms. Okay. With respect to the center frequency value, that is 50 ohms input impedance. Suppose if you consider the acceptable value as 48 ohms, then you have to get the frequencies at which the input impedance is 48 ohms. Suppose here it may be the 48 ohms and here it may be the 48 ohms. Okay. Now the range of frequencies, this is called, what is this? This is called the bandwidth. Okay. Fine. Like that it can be explained for all these parameters. Okay. Now for broadband antennas. Okay. Broadband and narrowband means suppose if the frequency response is like this. See, if the frequency response is like this, then it is called broadband. If the frequency response is like this, then it is called narrowband. Okay, for the broadband antennas, the frequency response is broader. And for the narrowband, the frequency response is narrower. So for broadband antennas, the bandwidth is expressed as a ratio of upper frequency to lower frequency. Okay, suppose if this is the response and here this is called upper cutoff frequency FH, and this is the lower cutoff frequency FL. Okay, at these points the values are at acceptable values with respect to the center frequency FC. This is the center frequency FC. FC or FR, I can call it as FR, resonant frequency. So for example, see here a 10:1 bandwidth means F upper is equal to 10 times of F lower. Okay, F upper is 10 times of F lower. FH is F upper and FL is F lower. And for narrowband antennas, the bandwidth is expressed as percentage. That is, percentage bandwidth is equal to F upper minus F lower by FC into 100. Okay. Example, a 5% bandwidth means the difference between upper and lower frequency is 5% of the center frequency. Okay. Then, why bandwidth is not unique? Why it is not, the bandwidth definition is not a general definition? Because different antenna characteristics, that is input impedance, pattern, gain, polarization, etc. do not vary in the same way with the frequency. That is the reason we can't generalize the definition of bandwidth. It can be defined at different places for different characteristics in different way. Okay. The specification depends on application requirements. Then we have two types of bandwidths, pattern bandwidth and impedance bandwidth. Pattern bandwidth is the bandwidth related to gain, side lobe level, beam width, polarization and beam direction. Okay, so means with respect to all these characteristics, if you define certain range of frequency within which all these values are acceptable values compared to, means with respect to the center frequency, then that bandwidth is called pattern bandwidth. Coming to the impedance bandwidth, it is related to input impedance and radiation efficiency. Okay, same way you can, like pattern bandwidth, you can define impedance bandwidth as the range of frequencies within which this input impedance and radiation efficiency are in acceptable values compared to the center frequency. Okay, then coming to the examples of different lengths of antennas and their bandwidths. First, we'll see the linear dipole. The linear dipole of length lambda by 2, pattern is insensitive to frequency. Means the pattern only depends on frequency. Means the bandwidth is limited by impedance and can be expressed in terms of Q. Means for linear dipole, we can define only the impedance bandwidth. It won't have pattern bandwidth because pattern is independent of frequency. Then coming to the large antennas whose dimensions are greater than lambda, Q, the quality factor Q is nearly unity, and bandwidth is usually formulated in terms of beam width, side lobe level and pattern characteristics. Means it has no impedance bandwidth, it has pattern bandwidth. Then coming to the third type, intermediate length antennas, bandwidth may be limited either by pattern or impedance. Means you can define both pattern bandwidth and impedance bandwidth for intermediate length antennas. Okay, then coming to a special case, very large bandwidths. Some antennas achieves extremely large bandwidths. Example, 40:1 or greater. 40:1 means the upper cutoff frequency is 40 times of the lower cutoff frequency. Imagine how much bandwidth it is. These are known as frequency independent antennas. The antennas whose bandwidths are very large are said to be frequency independent antennas. Examples, log periodic and spiral. Okay, this is about the beam efficiency and the bandwidth. Okay, thank you very much.